Okay, so this is the second hour, or the last hour, sorry, of Physics 1C, Physics 1A for March 1st. And we're going to try to do a couple more problems before we finish up today. And the first one we're going to look at is this ladder problem. So what we have is we have a ladder that's indicated by this rectangle right here that's leaning against a wall. It's 10 feet long, and it's 100 pounds. It's leaning against a smooth wall. So smooth kind of means frictionless, or very low friction. And it's sitting on a floor with a coefficient of static friction of 0.5. So the coefficient of static friction down here is 0.5. A 200-pound man climbs a distance x up the ladder as shown. So there's a little person that's trying to walk up this ladder. We want to do two things. We want to find the friction at the floor, and we want to find the maximum distance that the man can climb up the ladder. Those are the two things we want to solve for. So I've redrawn this over here. And what I'd like for all of you to do now... Oh, I have one more thing I got to draw my picture. I got to put first on there. I'd like for you all to try to just do your best and see if you can't draw all the forces acting on the ladder, if you could. Okay? So draw all forces acting on the ladder. Not the person, but on the ladder. I'll give you a couple minutes. Okay, that's been about 2 minutes. So, can anyone maybe just type in the chat what those forces would be? And I would say that there are 1, 2, 3, 4, 5 forces, I think. You can either type them out one by one, type them all out at the same time. What color are we going to use for the forces? I guess we use red again. Two weights, normal force, friction. Okay, so there's going to be a normal force at the ground, right? Right here. And there's going to be... I'm going to do all the arrows first. There's going to be a friction force, right? We don't really know what way it's going to go immediately, so let's hold off on that one. There's going to be the weight of the ladder, which is going to go right from the middle of the ladder. So the weight of the ladder is actually less than the weight of the person, isn't it? So that's going to be the weight of the ladder. We're going to have a weight for the person. And just do that. And then we can make it a little longer. There we go. Normal, weight of the ladder, weight of the person, And then what about this wall up here? Is there a normal force on this one? Yeah, force of the ladder or the wall. Or really it's the force of the wall on the ladder, right? Like that. Okay, let's label those. So we normally just call this, normal force right here, right? It's the force with the ground. Let's call the force from the wall, I don't want to call it W because we usually use that for weight, right? This is going to be the weight of the ladder. This will be the weight of the person. We'll just label over here what those are. So the weight of the ladder is given as 100 pounds. And the weight of the person is given by 200 pounds. We also have an angle that shows up here. So theta is 53.13. Pretty sure that same angle is going to show up right here. And because we will probably need it later on, I'm going to call that angle right there phi, which will also be this angle right here. And we'll just say phi is going to be the complement to that, which is 36.87. Okay, so we've got our normal force, the weight of the person, the weight of the ladder, the P. Now we got to throw in the friction force. What we said there's no friction up here because the wall is, quote, smooth. So what direction do we make the force of friction down here at the bottom? Is it going to go left or is it going to go right? Point to there, and then tell me why too. So you guys are saying right, but why would it be right? Because equilibrium, that's a great way to think about it. There needs to be some force to counterbalance this one, right? And this is the in terms of like the x, like if we call this the x direction, right? In the x direction, there is only one force right now, and it's pointing to the left. P is the force of the wall on the ladder. Yeah, the ladder naturally wants to go left. That's the other reason. So either you say that there needs to be some force to counterbalance P, or you say if the ladder were to start to slide, it would slide to the left. If you don't believe me, you can go test this yourself by taking like a pencil and putting it up against a wall, or if you got like a long ruler, you could put that up against a wall, and you could lean it, and you'll notice that as this angle gets smaller and smaller and smaller, eventually your object is going to want to slide to the left, because eventually there'll be too much torque from the weight pulling down on it. So that's the direction of our friction force. It is static friction, so we're going to label it F sub s. And now we've got all of our forces. Now this particular problem is really nice because the next step is kind of done for us. We also need to pick the x and y direction. So it's pretty natural if you look at the direction that all these forces are pointing to just say the y will be up and the x will be to the right. Stand on a ladder and wait until it falls. You can do that if you want to, but it's obviously kind of dangerous. Yeah, it's much easier to just if we were in the classroom, what I do is I lean a meter stick up against a wall and we kind of tap it until it fell, and then we'd calculate what the maximum. Okay. All right. So next step was to pick axes, break up components. We don't need to do any components here because everything is already pointing along one of our axes. So what's left is to just use our equations, basically. So our equations say, we'll start right here. Net force in the x direction is equal to 0. We'll have a net force in the y direction equal to 0 equation. And probably we'll write down here net torque equal to 0 equation. Okay, so net force in the x direction equal to 0. There are exactly two forces. There's P, which goes left, and friction force, which goes to the right. We said right was positive, so we'll have F sub s, the static friction force, minus the force from the wall is equal to 0. For the y direction, we're going to have the normal force goes up minus the two weights, which point down. So the weight of the person minus the weight of the ladder. Let me actually add one other thing in here. This distance is x out to where this person is, right? That distance is x. Okay. Looks like that's it right there. This actually allows us to exactly calculate what the normal force is, right? The normal force is going to be equal to the weight of the person, which was 200 pounds, plus the weight of the ladder, which is 100 pounds. So this is 300 pounds. Really simple. Right? That's our normal force. Now, for part A, it tells us to find the friction at the floor. And this is a little bit tricky because I think you need to make some assumptions about this statement right here. Part B says, find the maximum distance up the ladder the man can climb. So I would argue that if we assume that this person is already at the maximum distance that you can possibly climb, now we don't know what the value is, but if we assume that person is already at that point, then at that point, the friction force should be at maximum. Right? Because that's going to be the limiting factor. How far he can climb is dependent on how big the friction is here, right? So if we wanted to find the maximum distance he can climb, that's going to occur when the friction force reaches its maximum value. And if you remember our definition of the static friction force, I don't think we've done any problems with static friction yet, have we? Maybe we have, I don't know. Was that it was less than or equal to, not equal, but less than or equal to mu s multiplied by the normal force, but that the maximum value, if it's less than or equal to Fs max, occurs when this is equal to mu s times n. So I think we can use this and the normal force to now find what the value of the friction is. Does that seem reasonable to everyone? So technically, the value of the friction depends on how far he goes up, right? We could calculate the friction when he's not on the ladder if we want to, but that's not what the problem asks. So see, mu s was 0.5, and we're multiplying by the normal force, which was 300. So we end up getting that Fs max is equal to 150 pounds. And then we can plug that into this equation, right? We know from this equation that Fs max is equal to P, and that means that P has to then also be 150 pounds. Okay? Now we weren't asked to find this, but it might be useful for what we do next. Alrighty. So one thing left to do, find the maximum distance up the ladder the man can climb. Now I don't know if you've noticed this as we go through these problems. I'm trying to emphasize that the method by which you approach these problems is, hopefully this will make sense. You try your best to ignore what the question is in a way. Now you need to know what the question says, right? And you need to apply all of the statements that they make inside of the question, right? But if what your thought process now is, now that we found friction, if your thought process is, okay, now I need to calculate x, we are going to calculate x. But if you think, how do I calculate x, that is a very complicated question in and of itself. If you say, how do I find x? How do I find x? And what I'm trying to emphasize to you is that, like, you just use these equations. And this is all we know, right? We know that this is true, we know this is true, and we know this is true. That's all that physics tells us, right? So contained within this final equation that we haven't used yet must somehow be a solution for what this variable is, right? Does that make sense to everyone? Don't try to solve x. Just write down the equation. It has to give it to you because, assuming that everything else we wrote down was true, it's got to be in there somewhere. Don't even think about where it is. It has to be, right? Okay, so net torque equal to 0. Now, in order to use the torque equation, we need to define something to be positive. Maybe just to prove the point. In the last problem, we said clockwise was positive. In this problem, let's say that counterclockwise is positive, okay? It makes absolutely no difference what you choose. But for this one, let's just say counterclockwise is positive. Okay. Now, in this problem, there are all sorts of good choices for what we can use for our axis, but we still have to pick one. So, for example, we could choose this corner down here. We could choose this point up here. We could even choose something really silly, or seemingly silly, like this point right here. It turns out that every single one of those is going to give us the same answer somehow, right? So just because the distance x is already measured from this point right here, let's use that as our axis. But I encourage you to try one of the other ones and prove that you can get the same answer, because you can. Now, there's a lot of other value to choosing this axis right here, right? N and F sub s are already on that axis. They're not going to show up on our equation. We're only going to get the two weights and the force P. So let's start doing it. So net torque equal to 0. I'm saying counterclockwise is positive, so let's start with P. Remember, our definition of torque is going to be torque equal to RF times the sine of theta, right? So for P, what is our R going to be? What's the distance from the axis to point P in this case? We're going all the way from the axis down here out to here, so it's the full length. So it's 10 feet, basically, right? So I'll write 10 feet. So I'm going to use that tick mark for feet. Hopefully that's something you guys have seen before. So 10 feet, that little tick mark means feet, times P. You know what? For some reason, this looks better when I do it on a chalkboard. I'm actually just going to write the word feet out, because that looks bad. So let's just write the word feet out. So it's 10 feet for the length of the ladder, multiplied by P, and then multiplied by the sine of the angle basically between the ladder and P, which in this case is going to be theta. It's that angle right there. Okay, so that's our positive one. And now we're going to have something similar for WP and WL. But they're going to be negative, because they're going clockwise. So minus, what's the distance between the axis and where the person is? Well, that's what we're looking for. That's x, right? So it's x multiplied by the weight of the person, 200 pounds, and then also multiplied by the sine of the angle basically between the ladder and that weight, which in this case is phi, or that angle right there, 36.87. So times the sine of phi. Get rid of that little stroke mark there. And that's it. For the weight of the ladder, what's the distance between the axis and this point right here? 5 feet, because it's half, right? So it's 5 feet between there and there. So we'll do 5 feet multiplied by the weight of the ladder, and again times the sine of that same angle, phi. And then these should all sum to 0. We've already taken care of 1, 2, 3 forces, and the other two forces would be at a distance of 0, so they exert no torque about that axis. And there's our equation. And it has one unknown, which is x. So let's isolate and solve. We'll put everything on, so we'll move the x WP sine phi to the right-hand side. So we'll have 10 feet Okay, and then we'll just divide both sides by everything that's multiplied by x. Obviously, on the right-hand side, that'll cancel with that. And now let's just throw in all our numbers. So we have, oh, here, I was going to do this. There we go. So it's 10 feet times p sine theta. We found p was 150 pounds in part A. And we're doing this times the sine of theta. If you look up to the left up here, I think theta was 53.13. It's the bigger angle. And then minus 5 feet. Now, I don't know if when you all are doing your homework and stuff, you're writing these units on everything, but you probably should. I'm going to keep doing it. 5 times 100, and then sine of phi now. That's the other angle. And all of that is divided by WP sine phi. The weight of the person was 200 pounds. And then, sine of 36.87. So you want to throw all that junk into a calculator. And I'm willing to bet that that's the right answer. I'm going to say it's going to come out to be some 7.5 number. This is what you should get. Let's see if we can figure that out by just kind of thinking about this. So it's 150 times that's going to be 1500. And sine of 53, as we said, is 4 over 5. 500. Sine of this one is 3 over 5. We're dividing by 200. Sine of that guy is 3 over 5. So all the fifths cancel out. So it's basically 1500 times 4 is 6,000. Minus 500 times 3 is 1500. We divide all of that times 200 times 3 is 600. So 4,500 divided by 600, which is equal to 45 over 6. And 45 is like 3 times 15. And 6 is times 2. Yeah, you get 7.5. That's the right answer. Oh yeah, good point. It's not meters. That would be way longer. It'd be 3 times as long almost. So this is actually feet. Thank you very much. Very, very common mistake I'm going to make. I'll just put it, we'll get all the way to the end. I've been writing feet the whole time, and then the very last step I put meters because, I'm just so used to that. Anyway. Does that make sense? Does that make sense?
Why did you include the weight real quick? My bad.
For which part?
So I understand the formula was basically r sine theta, but it never included the weight.
No, it's r times f times sine theta.
Yeah, there is. Oh yeah, I remember that. Okay, my bad.
That's okay. Yeah. Good question. These problems are kind of hard. I really like these kind of problems, but yeah, that's exactly right, Hudson. The math makes sense. If you follow the steps, it's relatively, quote, easy. But you just need a lot of practice on getting the setup right and getting these vectors right. So that's a really good point you made, and I want to kind of piggyback off that to say that all that setup stuff we do at the beginning is the most important part in these problems. Just getting your forces in the right direction, labeling your angles properly. You know what it's like? It's like you ever watch those cooking shows or cooking things on YouTube? And the chef will always say that you want to have everything cut up in advance, what they call the mise en place, where all your celery and your onions and your carrots are all cut up and ready to go. That's what this is. It's like that. It's like your mise en place. You got to get everything set up. You get everything's ready to go, so that when you go to do the math just kind of naturally falls out of it. You know, it just automatically kind of falls out of it. But yeah, this setup is immensely important. You got to get the directions correct. Gordon Ramsay would be proud of this setup. It could be a lot cleaner though too, right? I mean, you look at this picture. Now it's a lot. I drew a lot bigger in this case because I wanted to make sure I didn't make the mistake I made in the previous problem. In the previous problem, what I did is kind of a no-no. I drew all of my forces on the diagram. What I really should have done is, even after doing that, I should have made a bigger diagram right here, in this open space right here, and then it probably would have been a little easier to see where all these equations came from. But yeah, that setup is really, really important that you just take your time with the setup. Like, I guess what I remember when I was doing these problems as a student is that I was really good at mathematics. Like, I was good at algebra and geometry and stuff like that. So I was really wanting to, like, kind of jump to the equations too early. And I would make all sorts of mistakes because I would do that. I mean, I still make mistakes. Mistakes are normal, but I meant, like, I couldn't even solve problems back then because I was trying so hard to get to this equation so I could start doing what I was comfortable with, which is the algebra. That I was forgetting that the setup itself is where all the important stuff is. So take your time. Read the problem carefully. Read it more than once. I think a lot of you have already seen in doing some of the homework that you could have probably figured it out if you just took a little more time to read it. Because like when you went back and you read the problem again, you noticed what your error was. So don't sleep on that. Make sure you're reading and rereading problems. And then... yeah, Hudson, that's because I was right in y'all's boat when I was, your age, right? I was exactly where you all were, where I thought this stuff was really, really hard. And I started to learn all these methods, and it makes it a little easier. But I promise that you will all get there. And by the time you're done with 1A, you're going to be masters of this stuff. And then you'll be able to go on to the other classes where things get a little trickier. I want to do one more, but we don't really have much time. I think we have 12 minutes left. And we can probably set one up in 12 minutes. Here, let's do that. So I thought this would end up going on the next page. The question is, which one do we do? I mean, this one's really good. Yeah, this is we have to do this one first because it kind of leads into this problem. So let's do it. Let's at least try to set this one up, and if we don't finish solving it today, we can finish solving it next time. Okay. I do not want to go too late though, so I will stop right at 5:10, no matter what we're doing. All right, a 50-pound table, 4 feet square and 3 feet tall, is dragged across the floor at constant velocity by a force of 20 pounds. Along the top, so you got a 50-foot table, it's dragged across the floor at a constant velocity by this force. So it's being pulled at 20 pounds, which is pointing along the tabletop and parallel to the ground. This should say center of gravity. This is C. Center of gravity is 1 foot directly below the center of the table surface. And again, that's kind of like where we're going to draw the weight. We want to find the coefficient of kinetic friction and the normal force on each leg. We want to find the minimum coefficient of friction such that the table is on the verge of tipping when being dragged at constant velocity. So they're two separate questions. This one. And two separate setups, too. So let's draw a picture, because I think it's kind of hard to visualize what's happening here. So what we have is, we've got a table. And what we'll do is, we'll just draw it basically two-dimensionally. So we've got a tabletop right here. And we've got 2 legs. Well, 4 legs, but we're just going to draw 2. We'll draw 1 here. And we'll actually put it right at the edge. So that's 1. There's 2. We also have the ground. Whoops. Shapes, line. Let's draw a line for the ground down here. And square it up the legs. Okay, so that's basically our table. And in case it's not like... Oh, I see what's going on. This line's not straight, is it? That looks more straight. There we go. So it's probably not completely straight, actually, still. Does it matter? I don't know. It's bothering me. What if I take off Alt? Well, that automatically... that's what I should have done. All right. No, that's not straight. That's straight. There we go. I just need to shorten it. Okay, so there's our table, and if you can't visualize how this is a table, I'll draw some other lines on here to make it clear how it is, but we're not going to use them. So think about, this is the tabletop. It goes back this direction. Like this. And then we draw one more line from here to here. And then we'd have legs, right? So there'd be a leg on the back over here. And there'd be a leg over here. And then, of course, the ground would be like that. But that's basically our table. So now that you can visualize it a table, is it okay if I take off these extra lines? So that's the tabletop on the top. Now let's assume that we're looking at it like basically straight on. Okay, so we don't worry about these lines. So we just drew them to kind of get an idea of what it would look like. Now imagine that we're looking directly at the table. So now we just see the front leg. The back leg is directly behind this one, and we just see the front leg over here, and again, the back leg's directly behind it. And now we can talk about what they're saying in the problem. It says a 50-pound table, so that's the weight of our table. It's 4 feet square and 3 feet tall, so we can actually come in here and say that it's 4 feet square on the top, which means that this is going to be 4 feet in this direction, and this will be 3 feet in this direction here. We also know the center of gravity is 1 foot directly below the table, so what we could do is we could come right about the middle here. That's about a foot beneath that, so a third of this distance. And we could go ahead and just draw on that first vector for the weight so that we know what that all means. So there's our weight. All right. Now, it may seem weird that the weight of the table is being drawn at a position, like this is an open area right here. Okay, it's not a box. This whole area underneath the purple line is open. You know, when you look under a table, it's open, right? It might help if I draw one more line here, too, actually. Let's give the table, like, a little bit of thickness to it. Okay, so that's kind of like the top, let's say, right there. But yeah, the center of mass is, like, kind of directly below the middle. All right, so it's saying it's being dragged across the floor at a constant velocity by a force of 20 pounds. So let's add onto here. And it says that that force is along the tabletop and parallel to the ground. So we'll have a force that goes this way. And I'm going to call that like a pulling force. We'll call it P and just say it's equal to 20 pounds. I think we can probably come in here and we can say that W is equal to 50. Okay, I think I've put all the information that's in the problem onto the picture. Does anyone have any questions before we start going? Okay, it says find the coefficient of kinetic friction and the normal force on each leg. So before we even get into solving that, we need to finish drawing our forces. So we've got weight and we've got P, right? The first step in all these problems is to draw all the forces acting on our table. Can anyone tell me what other forces are we going to have? This table is basically just being dragged to the right. You can think about it like this. Like, I guess I've got a coffee table, Mario. If I grab my coffee table underneath it and just pull it. Normal force and friction, right? How many normal forces do we need? We need one normal force for each leg, right? So let's draw those in. So there's going to be a normal force here. And... oops. So I can click copy paste. Give me a normal force over here. We'll call that like N1 and N2. So each leg has to support some weight. And then, of course, at each of those points, there's also going to be a friction force, which will point back this way because the table's being dragged to the right. So there's going to be a friction force back in that direction. So copy paste that one and put it over here as well. I haven't talked about the length of these yet, but I will here in a second. So we'll call this one the friction force on the front will just be F1, and the friction force on the back will be F2. Now you could rightly ask, well, why don't we have 4 normal forces? There should be one on the front leg, one on the back left leg, and then 2 over here as well, right? There's 4 legs, so it'd be 4 forces. We're just going to kind of assume that the normal force on the 2 legs that are toward the front are the same, and the normal force on the back 2 legs are going to be the same. We are not going to assume that these are equal to each other, though. Which one of these do you think will be bigger? The front normal force or the back normal force? And why? The front. Okay, you're right. The front's gonna be more. Why do you think it's more? Yeah, you just just think about it. Yeah, imagine yourself pulling a table, and it's mostly going to be like the front leg. That's where you're going to feel most of the friction, right? And yeah, it's going to kind of tip up in the back in general, right? And that's exactly what this problem's about. So not only will the normal force be bigger in the front, but the friction force will also be bigger, right? Okay. I think that's all the forces. So I believe what we can do, we have 3 minutes, is let's try to solve for the coefficient of kinetic friction and the normal force on each leg. So in this problem, we're not actually finding the friction force, although we can do that if we want to. We're actually trying to calculate what is the coefficient of friction. Now we're going to assume it's the same in both cases because coefficient of friction is related to materials, right? So if this is wood and this is carpet, we're going to kind of assume that we're going to have the same value. But what is that value? Now we can say some things here before we even go into that. We know that F1, the friction force in the front, should be equal to that coefficient of friction times N1, and F sub 2 should be equal to that coefficient of friction times N2. We're really running out of time, so I'm just going to briefly go directly into this. Now that we've drawn all of our forces, the next step is usually to define x and y directions. We'll call it the positive x direction. We'll call this the positive y direction. And then we use our equations, right? Net fx is equal to 0, net fy is equal to 0, and then net torque is equal to 0. Even though it's moving, these should all still be true because it's being dragged at a constant velocity. Constant velocity means that net force is equal to 0. So x direction, what do we have? We've got P minus F1 minus F2. And in the y direction, we've got N2 minus the weight minus N1 is equal to 0. This tells us that the weight is equal to N1 plus N2. And this one tells us that P is equal to F1 plus F2. But we know from over here that F1 is mu times N1. And F2 is mu times N2. So it turns out that we can actually factor these out. I'm so sorry. That is a positive. Thank you. Yeah, N2 is up, N1 is up, W is down. This equation is correct, though. This equation is correct. But thank you for noticing that, Ange. I apologize. And we're out of time. So this tells us that basically P is equal to mu times W, which means that mu is equal to P over W. We'll pick up from here next time, but we can pretty quickly see that 20 divided by 50 is equal to 0.4. And that's what the value is. Okay, we're going to stop there. And we're just going to come back and talk about this problem again. We'll probably start right from here, maybe refresh what we did here, and then we'll solve part B next time. Okay? So I'll see you all on Wednesday.